Okay, so here we are. We're going over independent events. We want to first of all we'll talk about the formulas for how you calculate probabilities for independent events. So here we go. We're going to look at this table here. As you know, I talked about this in the last video, but independent events, the probabilities have to not change just because the first event has already happened. So here we see this little formula that says, probability of A is equal to the probability of A given B. Remember I showed you that line, said it has to be a vertical line. That means A given B. So if B has already happened, then that takes away half of the events, or it takes away a portion of the set, and we only look inside of B, right? And we check the probability for A inside of B, and then we compare it to the probability of A overall. So here we're going to do that here. It says, let event A be the event that a flight arrives late. So here is A here, the late arrivals, right? First of all, we note that there is a total of 18 late flights. Okay, late arrivals. That's 18 flights that were late. Okay, that's event A. All right, I got it right here. Then it says, of these flights, I'm sorry. Oops. That's not true. There's 180 total flights. There's a total of 180 flights, okay? Then of these flights, there's a total of, we would say there's a total of 18 of the 180 that were late, okay? So the probability of A, what does that equal? Well, what it equals is, it turns out it equals like this. We would go the number of A, right, over the number in the set, which is equal to, we would say, so the number of A was, we said 18 over 180, right? And that is equal to, we can reduce that, and that's 1 over 10, okay? Which we can also say is 10%, okay? So now to find the probability of A given B, first we notice there's a total of how many B? Well, international flights, there are 60 international flights, right? Now, these flights, there's a total of how many late flights? Well, there are 6 of the 60, of just these 60. So that's what we're talking about when we say, given that B's happened. So if they told you, well, I know she was on an international flight, what's the probability of her being late? Well, if she's international, then there was a total of 6. So the probability of A given B, given that it was an international flight, so it's the number of A given, it's, let's see, that one, given B divided by the number of B, right, which is equal to 6 over 60, which is equal to 1 over 10. So that's also, we can express that as a percent. That's also 10%. So we compare these probabilities. We have 1 over 10 or 10% if she was just on a normal flight, and 1 over 10 or 10% if she was on this international flight. So we can conclude that a late arrival is independent of the flight being international, because the probability of being late is the same whether she is on an international flight or not. Okay, I don't know if I can actually, who cares about that, right? I'm trying to make this look nice again, but who cares? Okay, in the example, we compared the probability of A and the probability of A given B. Suppose you compare probability of B and the probability of B given A. Well, let's go back. So here we go. What is the probability of B? The probability is 60 over 180. Out of all the flights, 60 were international. So what is the probability that it was an international flight? Well, that would be 60 over 180, which reduces to 1 over 3. Now, given A, let's say it was a late arrival. What is the probability that it was an international flight if we know she was late? Well, we say, gosh, she was on a late flight. Must have been international. Well, let's check. International flights are 6 out of 18, right? Total lates. 6 late flights out of total 18 that are late are the international. So probability that it was international of the late arrivals is 6 over 18, which also is 1 over 3. Since this reduces to 1 over 3 and this reduces to 1 over 3, we can also conclude what? What this tells me is it tells me that it doesn't matter if she, I guess, being on an international flight does not change, or being late rather, right? Being late does not change the probability that she was international, or that the flight was international is probably what I should better say. Okay, so now it says you can use a tree diagram to help you understand the formula for the probability of independent events. For example, consider tossing a coin 2 times. The outcome of one toss does not affect the outcome of the other toss, so the events are independent. Tree diagram shows the probability of the coin landing upside on both tosses because this is one of 4 equally likely outcomes. So let's just take a look. So what we would do is we go over here like this and we would say, what happened on toss 1? And then what happened on toss 2? Well, did she get heads? Did she get tails? So let's say that in the case that the person got heads, then they could have gotten heads, and on the first one they could have gotten tails. So that was an option, right? Actually, these words here are dumb. I don't need these. Let me get rid of that. Okay, so that's one possible outcome. She could have got heads, and then she could have got heads again. She could have got tails, and she could have got tails again. She could have got tails, and she could have got heads again. Those are our outcomes. So this is, the tree would show actually branches. So we would put heads here. The first toss you get heads or tails, and then we would branch from heads to heads, tails, and heads, heads. And tails, tails, and tails, heads. So that's what it looks like there. I can't draw that here. I tried drawing with the, let's see if I can make this work, but I don't think so. So on the first toss, there's 2 outcomes, right? There's heads, and then there's tails. Let's see if this works. This is a tree diagram, right? And that's roll number 1 or flip number 2. Toss number 1. Toss number 2, she could get heads again, which would mean that she has heads on both of them. Or she could get tails again, and that could give her heads, tails. And here we have tails. She could get heads again. And yeah, that's, oh boy. So this is what, I can't use this pen here because it does this goofy stuff. If she gets tails, she could get tails again. So those are kind of the things that could happen. And that's what a tree looks like, that tree that they're talking about, okay? All right, so the probability of independent E is equal to the probability of A times the probability of B. Well, that's a really important thing to know. So we spin the spinner at right 2 times. Now, how do we do that? Remember, and that's where this comes in. I'm really sorry. We should have seen that. Maybe I'll even try drawing it again. Okay, so we have heads, and we have tails. Let's see if I can show you what I mean by this. And then those guys could have been heads, heads. Remember how we had it? And then we could have had heads, tails, right? And then this one, of course, she got tails the first time, so the second one could have been a heads. And the third and the fourth one could have been a tails. So if we just said rolling the dice once, the probability of getting heads was 1 out of 2. And then the second toss, the probability of getting heads is 1 out of 2, because she could have got heads or tails here, she could have got heads or tails there. So we have 1 out of 2 here, and on the second, this is the outcome of that first one, right? On the second roll, it was either heads or tails or heads and tails again. So again, 1 out of 2. But when you try to figure out multiple events, what's the probability, right? 1 group out of 2, or out of both the options. So what we'd say is that you would take, to find out the probability of getting that in both cases, we would take 1 out of 2, the probability of A getting ahead in the first toss, times the probability of getting ahead in the second toss. So the probability of A and B getting ahead the first time and getting ahead the second time is equal to the probability of A by itself, getting ahead by itself, which was 1 out of 2, and the probability of B, which was 1 out of 2, getting ahead by itself, the second roll. So that is 1 out of 4. Boy, I hope that makes sense. I know I've kind of talked around that a little bit, but that's how that works, okay? All right. So now it says you spin the spinner at the right 2 times. We don't have a spinner here. All right. And let's see if I've got an idea what the spinner would look like. Let's see. Okay, the spinner has 12 numbers on it. Equally divided, there's 12 numbers. So what is the probability you spin a number, an even number on the first spin, followed by an odd number on the second spin? So let's see, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the possibles. So how many to get an even number? Well, 1, 2, 3, 4, 5, 6 out of 12, which is 1/2. So getting an even number, so if we said event A, which is even on first, would be equal to 6 over 12, which is equal to 1/2. And then probability of B, which was odd on second, that would be 6 out of 12, because the other 6 are 1, 2, 3, 4, 5, 6. There are 6 there out of 12, which is also equal to 1 out of 6, okay, or 1/2, sorry. And we answer that question here. The probability of getting an even would be 1/2. The probability of getting odd on the second spin, 1/2. So the probability of A times B would be 1/2 times 1/2, okay? And so what does that work out to? It's 1/4. Okay, so the probability you spin an even number on the first spin followed by an odd number on the second spin is 1/4. It is simply found by calculating the probability of A and B separate and then multiplying. Now, what is the probability you spin an odd number on the first spin followed by an even number on the second spin? All right, well, odd was 1/2, right? Times 1/2 again for even, it's still going to be 1 out of 4. So what did we notice? It didn't matter if we said probability of B times the probability of A, we got the same answer. And so what did we notice? We noticed that the probabilities is commutative. Okay, and what that means is it doesn't matter the order we go in. Okay, we go probability of A times the probability of B. So here's the two-way table. It shows the data from the first example, right? Show that a flight arriving on time and a flight being a domestic flight are independent. Okay, so arriving on time and domestic. Okay, so here we go. Probability of A, probability of B, and probability of A and B, we have to notice that there's a total of 180 flights. There's a total of how many on-time flights? 162. So the probability of A equals 162 divided by 180. Okay, and then that reduces, let's try that, that's going to be 81 over 90, and then that would reduce to 9 over 10. So that's 81 over 90. Those are just even numbers, so I could divide that in half. 81 and 90, and I recognize those are both multiples of 9, so if I reduce by 9, 9 out of 10, right? Because 9 times 9 is 81, 9 times 10 is 90. So there is a 90%, or 90% of the flights are on time. Okay? Or out of the 180 flights, 90% of them were on time. Okay, so 9 out of 10 probability. Now, how many total domestic flights? There were a total of 120 domestic flights. And there is a total of how many on-time domestic flights? That would be 108. So the probability of B, is 120 divided by 180, which is 1 over 3. Okay. And then the probability, it's 2 over 3. Probability that the flight was domestic, there were 120 of them, so that's 2 over 3. Now the probability of A and B, which is the probability of A times the probability of B. So the probability of A we said was 9 out of 10, and the probability of B was 2 out of 3. And so when we multiply these, we get 18 over 30, which is equal to, let's see, I can reduce 6 over 10, which is equal to 3 out of 5. So the events are independent because, did we get the same probability either way? Did I do something wrong here? Right. A total 180 flights. There's a total how many on time? 162. So 162, that decimal point doesn't need to be there. 162 divided by 180 is equal to 81 or 9. That's 9/10, right? And there's a total of 120 domestic flights out of 180, right? That came up from 120 out of 180, which is equal to 2/3. And then there's a total of on-time domestic flights. Oh, I didn't finish that part. So the probability of that would be 108 divided by 180. Sorry about this, which is equal to, well, those are both, I can do 54 divided by 90. I can divide those in half pretty easy. And then those are both multiples. These are both multiples of 9. So if I divide by 9, I get 6 over 10. And then, of course, that's 3 over 5. So now when we calculated this odds, it was A and B being domestic and on time. The probability was 108 out of 180. And when we did just domestic and just on time and just domestic, we got the same exact thing. So the events are independent because the probability of B times the probability of A, was it A? Oh boy. I'm going to put it like this. Probability of domestic. No, wait. The first one we looked at was what? On time times the probability of domestic equal the probability of on time and domestic. Okay? So a different way you can show a flight arriving on time and a flight being domestic are independent events. Okay, I'm going to skip that right now. This is going longer than I really want it to. But I think you get the idea, and the rest of this down here is practice, and you're going to get a chance to practice really on Khan Academy. So I will go ahead and wrap this up.